This video is going to be about horizontal projectile motion. So in the last unit, we studied one-dimensional motion where the objects were moving in a straight line, either a horizontal line or a vertical line in the case of free fall. In this unit, what we're going to do is we're going to focus on projectile motion. So these will be objects that are flying through the air, but the only force acting on them is the force of gravity. And these have a very specific type of motion, and there's a very specific way to analyze this motion as well. And so the way we start this unit is we kind of simplify it, and we look at the simplest type of projectile motion, and that's where the object originally is launched horizontally. Okay, so in other words, it's not being launched up at an angle or down at an angle. It's like a ball rolling off a table. It's going to have its initial velocity, and that initial velocity will be in the horizontal direction. So the case we're going to look at, there's this poor guy. He is ready to drive off the cliff, and so he has some velocity v naught, and it's perfectly horizontal with the cliff. And so what's going to happen is he will slowly but surely, we kind of what's going to happen. So, he's going to go, and eventually he's going to go and hit the bottom. Okay, and so what we want to do is we want to be able to calculate a few things. We want to be able to calculate maybe how far he's going to go before he hits the bottom. So maybe this is called the range. So maybe from here over to here. And when we work these problems, it's going to be very useful for us to think in terms of this is a horizontal thing or this is a vertical thing. So in this case, I'm going to say that this is a horizontal displacement. Okay, this actually probably should go up a little bit further here. So all the way to the end where he's going to hit would be my horizontal displacement. And then I can also imagine that there's this vertical displacement, which would be, in this case, the height of a cliff. So delta x may be v. All right. These are the types of things that we pay attention to when we analyze these problems. And so what's going to happen is the velocity is going to change with time. So it's not going to stay in the same line. It's always going to be kind of tangent to this curve. We also know that's going to get larger and larger in magnitude as time goes on. Now, when we look at this velocity, what we'll notice, and unfortunately probably should be more careful with the scale, but what we'll notice is that the only acceleration we have is the acceleration due to gravity, which is pointing down. And each one of these velocities can be viewed as consisting of two components. So now our work with components is going to come back. And so the components that we're going to look at is we'll have, for each one of these, we'll have a horizontal component, and then we'll have a vertical component. And over here, whoops, let's go back one. Okay, and over here, we will also have a horizontal component, and we will have a vertical component. And then finally over here, we'll have a horizontal component, and we'll have a vertical component. Okay, and so this will be true all the way until right before it hits the ground. Now, as I said, if this was to scale, might be a little bit easier to see, but the fact is since our acceleration is in the vertical direction, okay, then this, let me change my colors here, this horizontal component will not change. Acceleration is a change in velocity. Well, the only component of the velocities that will be changing with time are these vertical components. Okay, the horizontal component won't change at all. And so when we look at these problems, that's what we're going to see. We're going to treat the horizontal motion as a constant velocity type of motion. And we're going to treat the vertical motion as accelerated motion, much like free fall. And it turns out that the time it takes for this car to hit the ground will only depend on how high above the ground it left the cliff, or how high the cliff is. It doesn't matter how fast it was going horizontally when it left the cliff. And that seems kind of counterintuitive to us, because we know if it's traveling faster horizontally, then this curve would be longer, right? And so there's going to be a greater distance. But the fact remains is that the time it takes to hit the ground will only depend on this vertical distance it has to fall. It'll actually hit the ground at the same time as if you took just a rock and dropped it off the cliff straight down. Okay, those two will take the exact same time to hit the ground. And then, knowing the time, how long it takes to hit the ground, we can then say, okay, well, that's how long it has to move horizontally. So if we know the horizontal component, which we do in this case because it's essentially what it drove off the cliff with, if we know the time it takes from this vertical motion, then we can also use that and say that this will just be my horizontal component times the time it's in the air for. Okay, so I mean that's the gist of it, guys. That's kind of the key concept to this. And so all this chapter will be just dealing with this idea of components and the fact that we can treat the components separately. The biggest mistake I see students make on this is that they'll use vertical things to solve for horizontal quantities. So they'll use like G in an equation when they're trying to solve for this horizontal distance. Okay, don't do that. You will get the problem wrong and you'll be very sad. Okay, so to kind of summarize things a little bit here, horizontal motion, as I said, this horizontal motion, okay, it'll be constant the entire time. Okay, and this obviously is in the absence of like air resistance or a headwind or anything pushing it or accelerating it in the horizontal direction. So it's constant the entire time. The equation that we use for it will be delta x horizontal is equal to this horizontal component times the time that's it's in the air for. And if you look at this horizontal position over time, as I said, it's a constant velocity motion. So what you'll see is this nice straight diagonal line, because the slope is constant and this is just time graph and I have a constant velocity. And if I look at the horizontal velocity versus time, we'll have a nice just straight line here. The acceleration is 0, so it's flat. The vertical motion, however, this will changes due to this acceleration due to gravity g. We actually must use our kinematic equations to solve for it. Okay. And if we were to look at the vertical position versus time, because it is accelerated, you'd start off at maybe some height. If you're above the ground, you start at some height, and it would actually accelerate. It would curve down. It would change. This velocity, this instantaneous velocity, would become greater and greater over time. Okay, so kind of showing you what the slopes of the tangent lines there. And then if I were to plot the vertical velocity versus time, it's going to start off at 0, and it's going to be a nice horizontal line, and this slope is g. Okay, this slope is the acceleration due to gravity g. Okay, so in class we'll work problems with this. Okay, I'm going to show you an example problem and kind of how this all fits together. But these are the concepts. These are the concepts involved with horizontal motion, and they also apply to angled motion. The only difference is that with angled motion, instead of having this velocity just be totally horizontal, you would have some initial vertical velocity as well as horizontal velocity because of the angle, and that's really it. So anyway, that's your introduction to projectile motion, and like I said, we'll work problems in as a class. I'll do a sample problem and kind of show you how this all fits together. And if you have any questions, let me know.